Okay, welcome to the second lesson on compound interest, but we're getting towards the near the end of our unit here, and so we're talking about something new. It's called an annuity. An annuity, and we're going to learn pretty quickly that an annuity is just a series of compound interest payments, and so the learning targets that we're going to do today, we're actually going to do 3 of them. Is calculate the future value or present value of a regular payment or investment or loan. So the key is the regular payment. Write a timeline series for an annuity and calculate the payment. So we're going to see that as R, but PMT will be the other way we see it. But either way, it's the payment. So the first question that we're going to look at is, suppose you invested $100 at the end of each month for 4 months at 3% per year compounded monthly, according to the following timeline. So the end of every month, we're putting in $100. And we're doing it at an interest rate of 3% per year compounded monthly. How much would you have saved at the end of 4 months? So if you look at this question, you can actually do this question based on the little formula that we've given before, the compound interest formula. And so what we have is $100, and we have to decide that it's actually been in the account. How long has it been in the account for? And so the way we answer this question is, for each one of these 4 payments, we actually just calculate the interest at the end of the 4 months. But it does require, the timeline is very helpful because it does show us how long each one of the payments has been in the account for. And that's going to be really important because that'll tell us how much interest each one grows. So the first one is the interest rate has to be 3% divided by 12. So we always divide the 3 by 100 first, and then we divide it by 12 to get the number. And so this is actually going to be a 0.25% per month, which makes sense because it's 3% per year. So how much money you have at the end of the 4 months? The first payment has actually been in the account for 3 months. And so like the $100, 1.0025 to the 3. The second one is so that's the first one. The second one is actually only in the account for 2 months, and so these little lines here just denote the 2 months that it's been in the account, and so we use the exponent to the 2. But that's the compound interest formula. The second last one is only in the account for 1 month, and so it's only to the exponent 1. And the last one actually just got there. It hasn't actually been in the account for any time. It's just the 100. And so all we have to do to answer this question is just add up all 4 of these numbers. So you can calculate them and add them up. So we're going to look at a question. I just changed that because I made a mistake in the answer. I read it as 6. I read it as 5, but it was 6 in the note. So I just changed that to a 5 there. You deposit $1,000 at the end of each year into an account that pays 5% interest compounded annually. How much money will be in the account after 5 years? Draw a timeline and the series that we would have to add. So you do think about the same kind of thing. The interest rate is 0.05. It actually is 5% because it's compounded annually. So we don't have to divide it with just the 0.05. The N is going to be 5. So that's just saying that there's going to be 5 payments. And we're going to see that in the formula. So we call that N, which equals 5. Our timeline looks something like this: 0, 1, 2, 3, 4, 5, with $1,000 showing at the end of every year. And so this is what we're expecting when we ask for a timeline, just to show where the payments are and how many payments there are. So the first one's actually worth $1,000 times 1.05 to the 4. It's actually been in the account 4 times. 1, 2, 3, 4. The second one is 1,000 times 1.05 to the 3. The third one is 1,000 times 1.05 to the 2. And to the 1, and then again it just got there, so it's just 1,000. And then we just add up each of these 5 payments. Now you'll notice that this is probably not something we want to continue to do. It's only 5 payments, but it's probably an inefficient way. And in fact, there's actually a formula that will add this up for us. But I'd like to show just what we're actually doing if we wanted to do it by hand. And then the formula is just kind of like bonus. It's just a faster way to do it. An Excel spreadsheet would do this a lot faster, would do this right away as well. It could do it the long way. But the formula is actually going to be very helpful for us. So let's look at the formula. The formula for present value, or sorry, for future value of an accumulated annuity. So the amount in the future looks like this. R is the regular payment, I is just like in compound interest, and N is just like in compound interest, the number of periods. So we can go back and actually calculate that, but we're going to do that in a new example. Johnny's been putting $100 in the savings at the end of every month since the start of grade 9. And 4 years later, he wants to go away to university. The account pays 4% per year, compound monthly. We're going to draw a timeline in this series. So R is the regular payment's 100. A is what we're looking for, the future value. And then the interest rate is 4% divided by 12. And we just don't round it to 3, like use as many 3s as you can, use the line over it, and just write it as many 3s as you can. We're going to do this for 48 months. So for the timeline, we don't actually want to draw 48 dashes. It looks something like this. Just draw the first 2 and the last 2. No matter how big the timeline is, it could be for 10 years. We just draw the first 2 and the last 2. And the $100 shows up at the end of every month for those 48 months. So just one at a time, the first 100 has been in the account for 47 months. The second one's 46. The second last one is just once, and the last one is just got there. It's $100. And so what the formula to add it up is, it looks like this. This is the sum of a geometric series. It's the same formula that we use to add up a geometric series. And it just does it a lot quicker for us. And we get an answer of $5,195. Be really careful here, like if you need to do more work, if you need to show your work here, just take these numbers one at a time, or you can just do it all at once. It all depends on your calculator and really what you're comfortable doing. But make sure that you can just do that and get the answer in your calculator, because we want to be able to get that. The other way, like we're actually going to look at it, and we often see this in a loan, is a present value annuity. And so like sometimes we actually want to find out how much is a loan worth today, or what's the regular payment on a loan that pays us off this much at the beginning. So the future value is not really helpful, because we know that we don't want to know what it is in the future. Like we know that the loan is paid off in the future. So we actually want the answer for how much is it worth today? What's the loan today? What's the regular payment today? So our formula for that looks something like this. It looks very similar, except there's a negative exponent on the end, and it's 1 minus instead of something minus 1. But you still have 1 plus I on the top and I on the bottom. We'll also see this. We'll also call this like PV. I prefer PV to P. I meant to change that, but so we just. But the big way you can tell the difference is this negative exponent. We're actually going to see we use this when we want to bring the payments back to the beginning of the timeline, versus bring these payments to the end of the timeline to find out what they're worth. That's why we use positive exponents. But for this one, if we actually wanted to find out if this was a loan we were paying $100 a month for, what's the loan for, we'd bring these back to the beginning. That would be a negative exponent, or be dividing. So that's the really thing that gives away that you want to use the negative, and that's why the timeline's so helpful. So just a couple more examples. This one is a little bit long, this lesson. Bob bought a used car, paid it for it in monthly installments of $400. Car dealership pays 8% per year, compounded monthly. What was the purchase price of the car? How much interest did Bob end up paying? I forgot to actually answer this second question, so I'm just going to talk about that. So we're going to draw a timeline in this series we'd have to add. Okay. So this isn't the most realistic question. We probably know the purchase price of the car. We would more so want to find out what the regular payment is, but it's easier to discuss this using the formula, just solving for PV, and then in the next example we'll solve for the regular payment. And realizing like that's the case where you're trying to find out what the regular payment is, and you know what the car costs. When you would solve for PV more realistically is like if you actually have a promise to pay. So somebody owes you money and you know how much they're going to pay you every month. Well, that's worth a certain amount of money now. If you want your money now, we have to calculate the present value of that promise to pay you is worth. And so and you could potentially sell that off to somebody else, and it's an investment for that other person. Okay, so the regular payment's $400. The interest rate is 8% divided by 12, and we do it for 36 months. We draw out the timeline. $400 at the top. Each one of them is going back to the beginning, and so to bring it back to the beginning, we can show the work for this, but it's dividing by the interest rate. If we're multiplying by the interest rate to go this way, we're dividing by the interest rate to go back to the beginning. So the second one, we divide it by it twice, and I really like the negative idea because it's really showing like going back in time. And then the second last one is 35 times it's going back, and the last one is 36 times going back. And the formula for that, just be very careful here. It's a little bit trickier to use than the other one because of the negative exponent. I like to do this part first, and then change it to negative and add 1, divide by this, and multiply by that. But just make sure you can do that so that you get the answer 12,764. Now I just ask you to listen carefully to me because I forgot to answer the second part of the question on the PowerPoint. If Bob and how much interest did Bob end up paying is answered by the question, how much did Bob pay? And so how much did Bob pay is 400 plus 400 plus 400 plus 400 36 times. So that's a total of $14,400. He paid out of pocket $14,400. How much interest did he pay? Well, if he had bought the car right at the beginning, he would have only paid $12,764. So everything else is interest. So to answer this question, how much interest did he pay? Find out first how much he paid. And there's no formula to it. We're just multiplying 400 by 36. And we subtract the present value, subtract how much the car costs originally. The last one here, Mrs. Snyder had 17,000 OSAP loans. This is more realistic. She wants to find her monthly payment for 2 years at 8.5% compound monthly. So the things we know are the 17,000 is the present value. We know it's present value because we want to bring all the payments back to the beginning. We want to find out what it's worth at the beginning. We do it for an interest rate of 8.5 divided by 12. We round that by going to the repeated decimal, and you're always going to get a repeated decimal here. It's just the way rational numbers work. Going to the repeated decimal just makes sure that you are as accurate as possible. Okay. If you're really annoyed by that, 0.00708 is not gonna be that harmful. It's just not as accurate. Sub it into the formula just like we did before. It kind of looks ugly, but it's really just subbing the numbers that we have into the formula. Remember, there's a one plus on top and not on the bottom. Now we make sure we carefully calculate this part. It's easier if you do that than try to figure out how to get R. So the easiest way to do this is carefully calculate this part. We get roughly 22. And if we divide 17,000 by 22, we get $772.75. So that would be our monthly payment every month to actually pay off the loan in 2 years. It's a really aggressive way to pay off the loan. But if she can afford it, then it's a great it's a great idea. Okay. So some practice. I divided this up. Just want to talk about how I divided this up. We're going to target 9 as your timeline. They're actually for the present value. I feel like the textbook dropped the ball a little bit in mixing these, in like separating these two pages. Like these are the future value ones, these are the present value ones. And same with these. These are the future value ones, these are present value ones. And these are the ones where you solve for the PMT or the regular payment. So these are the ones where you solve for R. These are the ones where you solve for PV or FV. I really think it's important that you know how to like distinguish when you're like which formula to choose. So make sure, even though you know what page it's on, to ask yourself, does it make sense that I use this formula? Okay, that's it.